Okay, assalamu alaikum and good morning. Today we start with another important topic, simplification of force and couple system. We know a system or a body may consist of many forces and couples, forces and moments. So in order to analyze the system, we try to simplify it by converting into a single resultant force system or single resultant moment system. Okay, so that is the first step. And how we can further simplify it to overall a single resultant force system. All the forces and moments are now converted into a single equivalent force. So how to do that? So first we start with simplification of the given force and couple system. Then we go to converting it into a single equivalent force system. Also we will be dealing with the equilibrium of forces and support reactions in the rigid bodies. Okay, in today's lecture class. Suppose you consider a rod. It is being held in one point B and pulled at point A. Okay, so there is a force applied at point A. So how to transmit the force to point B? How to transmit the pull. It is being pulled at point A and held at point B. Okay, it is like that. Now we are going to apply the force, going to transmit the force from point A to point B. From point A to point B. How to transmit the force? How will you transmit the force? How will you transmit the force? No? Like this. We add two forces here. You can see one force opposite to the force applied at point A, another force in the same direction of force at point A. So the opposite forces will get cancelled and we will have only one force at point F. So by adding two forces, one parallel to the force, and you can say equivalent to force at point A, another minus F. Equal but opposite to force at point A. So the opposite force is this force and the other force will get cancelled. Now we will have only one force at B. So force got transmitted to point B now. So for transmission of forces from point A to point B, we add two forces at point A equal and opposite to the force at point A. Two forces at point B equal and opposite to force at point A. Okay. So same amount, same direction but opposite sense. So forces, one sense and other one opposite sense is added here. So the equal and opposite forces get cancelled. We'll get only one force remaining. Like this, we add two forces. This green color force is parallel to our force F. The red one is opposite to force at point A. So the opposite red force and the force at point A will get cancelled because they are equal and opposite. We will have only the green vector shown here. Only one force exists. Okay. So we got the force transmitted to point B. Suppose, like this is the final one. Suppose if you have the force vertically applied at point A. So what will happen? If you want to transmit in the same procedure, what will happen now? So we follow the same procedure. We apply a force equal and opposite. Two forces equal and opposite to force at point A. So the forces in opposite direction may get cancelled. This force and this force will get cancelled, but it will introduce a couple now. It will introduce a couple. In the process of cancelling the force at point F, we introduce a couple. So we have a force and couple. Now it has been changed into single force and couple system. So we have a force at point F, force at point B as well as a moment is developed due to the couple. That moment will be equals to F times D, the distance between point A and B. So if you try to transmit a vertical force from point A to point B, it will introduce a moment also. It will introduce a moment also. If you apply the same procedure here, you have many forces, force F1, F2 and another moment. So F1 and F2, they will produce moments. Also there is a moment applied here. First we find out the resultant of the forces. So we first transmit all the forces to a single point. If you transmit all the forces to a single point, so the forces will produce a moment, similar to our case 2. Okay. If you transmit all the forces to a single point O, in order to bring the system to a concurrent force system. What do you mean by a concurrent force system? All the forces will be acting at a single point. So in order to bring these forces, there are many forces, all these forces, F1, F2, etc. So a single point O, in order to transmit it, we introduce a moment also. When you transmit it, it will introduce a moment also. So now we have to find out the resultant for all the moments. So we have a resultant force and also a resultant moment. So many force and moment system now get converted into single force and moment system. Okay. So transmission of force, if it is in the same direction, okay, it will produce a resultant force. But transmission of force in the vertical direction, it will have a moment developed. Okay. So we have to consider this. Yeah. Okay. Other transmit control. We are transmitting it. We are transmitting all the forces to a single point. Similar to this. Point A has a force. That force is now get transmitted to point B. Only one force we have. Only one force. In the first case, we have only one force. Point A, we have only one force. That force gets transmitted to point B. Just we move the force, transmissibility. Okay. So we move the force from point A to point B. When it is moved along the same line, okay, when we move along the same line, it doesn't matter. It will not have any. It will not produce any moment. According to the principle of transmissibility, it is like a sliding vector. The force, if it is moved along the same line of action of the force and the movement along which we are moving, are same, then it will not introduce a moment. But here, line of action is vertical. Okay, the line of action of the force is vertical. The line of movement is horizontal. So when you move like that, it will produce a force. When you transmit the force, it produces a moment also. We got the force transmitted, we have got force transmitted, but it will introduce a moment. If the line of action and line of movement is different. Okay. Here, these forces are inclined in different directions. So automatically, when you transmit to a single point, force F from here is getting transmitted to point O. F2 also transmitted to point O. So when you transmit it, it will introduce a moment also. So we have to find out the resultant for all the forces, all the transmitted forces, also the moment developed due to transmission. Okay. So this is called single resultant force moment system. For example, we have a case. It has got subjected with one vertical force and two inclined forces. Now we have to transmit all the forces to point O. So first, we find out the horizontal and vertical components for all the forces or the inclined forces. Okay, so the horizontal and vertical component can be resolved and find out what is the x direction, what is the forces in y direction. Then we have to find out the resultant force, value of the resultant force. Sigma, this will be using the Pythagoras theorem. It is a coplanar system. The forces are existing in a single plane. Okay. So first we resolve the inclined forces. Two inclined forces we have. This is a vertical force, parallel y direction. So x is the horizontal direction, y is the vertical direction. It is negative y, okay, downwards, y direction. This is inclined. This force is also inclined to 30 degrees. The angle is given here, the slopes are given here. So we have to resolve the two inclined forces into horizontal and vertical components. Then add up all the horizontal components of the force, all the vertical components of the force. then use the Pythagoras theorem to find out the resultant force. So that is the first step. First we find out resultant of all the forces. Okay. First we find out the summation of all resultant of all the forces. So we represent all the forces to a single force. And its direction can be obtained as 49.3. Okay. Sigma, theta, the direction of the resultant force will be tan inverse of Fry divided by Frx. Resultant y component divided by resultant x component. So that will give you the angle of your force. After that, we have to transmit all to. So when you try to transmit it, it will produce a moment. So that moment can be obtained by taking moment of each forces with respect to O. So we are transmitting all the forces to a single point O. Okay. So when you transmit it, it will produce a moment. So what is the amount of moment produced by each point, each force? Okay, that can be obtained by taking moment about O. So this is the vertical force. It takes moment about O. So the force times the distance, the perpendicular distance, 0.2. Say for example this force, 3 kilonewton sin 30 times t. D is 0.2. Okay. So we consider the moment developed in clockwise direction as negative, anti-clockwise as positive. That is why we put a symbol, conventional symbol here. So anti-clockwise considered as positive. Okay. So this first force, it produces anti-clockwise moment, so it is positive. Whereas if you consider the second force, it produces a moment in the clockwise direction. So 3 kilonewton cos 30 times its perpendicular distance is 0.1. So it will be negative. Then this force, 3 by 5 kilonewton times 0.1, it is again anti-clockwise, positive. Whereas 4 by 5 kilonewton, the vertical force is clockwise, so negative. Then this force is also producing a moment in clockwise direction, 4 kilonewton times perpendicular distance, 0.2. Okay, so force times its perpendicular distance from the point around which we are taking moment. O is the point of our consideration. That means we transmit all the forces to point O. That is why we take moment of all the forces about O. Okay, so we consider each force and its perpendicular distance. Each force and its perpendicular distance. So if you consider this 3 kilonewton force, its perpendicular distance is 0.2 meters. And the force arrow is facing upwards. This force acts like this, perpendicular distance is like this. So moment will be in anti-clockwise direction. Anti-clockwise. Okay. Whereas this force, 3 kilonewton cos 30, its perpendicular distance is 0.1 meters. It produces a moment in the clockwise direction. Arrow head is here. Okay. This perpendicular distance is here. So consider this as a bell crank lever. So this lever will rotate in this direction. So clockwise. That is why we have a negative sign here. Similarly, consider here also here we have got the equation for resultant moment. So the resultant moment will be 2.46 kilonewton meter, and it's positive. Is it positive or negative? It's negative, so it will be clockwise. If the answer is negative, we say that 2.46 kilonewton meter in clockwise direction. So we transmit all the forces to point O. First we find out the resultant force, then we find out the resultant moment. Okay? Any doubt? You can note down. Components. So sigma fx, sigma fy, then root of sigma fx square plus sigma fy square will give you the resultant. Then tan inverse of sigma fy by sigma fx will give you the theta also. So we can find out the resultant, but the resultant will be passing through the same O because it is a concurrent system of forces. Okay, this is one case. Suppose if they are not concurrent, you have a force like this, force acting at different points, but they are coplanar, acting in the same plane. So the resultant should also lie on the same plane. We have to transmit all the forces to a single point of our interest, say point O. When you transmit, it produces a moment. The resultant moment and resultant force we convert all the like the problem example we have seen. First we find out the resultant force, then we also find out moment produced by each forces about O. Since we are transmitting it to point O, we find the moment developed by each force about O. So the resultant moment also obtained now. Resultant force and resultant moment are shown. Now we convert this resultant force and resultant moment into a single force, single equivalent force. We know the resultant moment is given by F times D, F into D. Force times its perpendicular distance. Okay. These are the forces, resultant of the forces which gives the moment, Okay. So we move this force to a particular distance so that the force times distance will be equivalent to this moment. So if you know Mr, the magnitude of Mr, if we know the magnitude of Fr, D can be found. Value of Fr is known, value of M, resultant moment is known. So M equals to F times D. So M by F will give you D. The distance to which we have to move the force so that it will be equivalent to, it will be compensating the moment which we have. So we move it to a distance D. D can be obtained from the equation MRO, resultant moment about O divided by Fr will give you the distance D. So we convert all the forces and moment to a single equivalent force. We have a third case. The forces are parallel to each other. They are not in same plane. Okay, they are perpendicular to a plane. They are parallel. So each force may be at different planes. Okay, parallel to y-axis, for example. So we have to find out the resultant force Fr, which would be acting through O, and it will produce a moment. Each force will produce a moment, and the resultant moment will be about O. Okay, like this. Now we convert into a single equivalent system by moving the force to distance D in the perpendicular axis. We have three axes, X and Y. So this is Z axis, this is Y axis, this is X axis. So the forces are parallel to our Z axis or Y axis, we can say perpendicular axis. Then its moment will be in this axis, on the plane. Moment will be on the axis, parallel to the plane, on the plane. Now perpendicular to that moment axis, we consider another X axis, and you move the force to a particular distance. So it will have a moment equivalent to that moment developed because of all the forces. So we convert it into a single force system by moving it to a single, moving it to distance D. We convert it into a single force system. Okay, because the forces are not in same plane. They are not coplanar. They are parallel. First we find out the resultant force, also the resultant moment because of each forces. Then move the force to a distance D. The D is equivalent to Mr by Fr. But in the axis, perpendicular to the two axes. One axis is parallel to the force direction. The other axis is about which the resultant moment acts. But perpendicular to the two axes, we have to consider the third axis and consider the point of action of force at the distance D. Okay. So this will be equivalent to the system, first system. So these are the three cases we have. Either it may be concurrent forces or coplanar system of forces or non-coplanar system. So this can be found by sigma Mr by Fr. D equals to sigma Mr by Fr. Now we come to some examples for single equivalent. This is another case, special case. We say we have a distributed loading. The force is not a point load as we have seen so far. Okay, point load or we say concentrated load. This is a distributed loading. Load is distributed throughout the length of the beam or the member. Okay, so load is distributed throughout the length. We call it as uniformly distributed load. We have to convert this uniformly distributed load into a single load. single force. Uniformly distributed force system. This is given as 6 kilonewton per meter. That is, force acting is 6 kilonewton per every meter of length, every unit of the length, every meter of the length. Okay, that is why we call it as uniformly distributed load. Every meter it has got 6 kilonewton of force per meter. Okay. So how to find out the single equivalent force? First, we find out the total force for the whole member. So to find the total force, 6 kilonewton times the total length of the member we consider. 6 kilonewton times 6. So 36 kilonewton is the total net force acting on the beam. Net force acting on the beam, and it will be acting at the middle of the beam. Middle of the area along which the distribution of force is given. In this case, distribution is throughout the length. Okay, so we consider the total length. Suppose it may be partial also. It may be between A and B also. It may be the case where the distribution is only between A and B. In that case, the total force is 6 times 3, 18 kilonewton. 18 kilonewton only. Okay, and it will be acting at the middle of AB. Or it may be the left portion, 1.5 meters. 6 times 1.5, so 9 kilonewton per meter, and it will be acting at the middle of the overhanging portion. So like that. So what is the length of distribution? At the middle of the length of distribution, we will have the concentrated force acting, the equivalent force acting. So we convert. So this is distributed system. It is an uniformly distributed load. We have to convert it into a single force whose magnitude is equivalent to magnitude of the UDL, uniformly distributed loading, times the length along which it is distributed, and its position would be middle of the length along which it is distributed. So the magnitude is 6 times 6, 36 kilonewton meter, and it will be here. So at 3 meters, middle of your 6 meters length beam. Okay. This is one case. No problem. Okay. So we have another force system. Here we call it as variably distributed load, VDL. Variably distributed loading. So at the left point it is 0. The load is 0. At the right extreme it is 1440 Newton per meter. Okay. And this in general the loading is 160x Newton per meter. X refers to the length of the beam. So how to convert it into single equivalent force? We consider the area of the triangle. First we find out the net force acting on the beam. Net force will be area of the distributed loading. Okay, area of the triangle. Distributed loading is the triangular shape. So we have to consider area of the triangle half BH. Half B is 1440, height is 9 meters. Okay, so half BH will give you the total force, net force acting on the beam, and it will be acting at the centroid of the triangle. Centroid, we will see about centroid in detail in our next unit. So the centroid, okay, is where your load is concentrated, mass, center of gravity or centroid, okay, center of mass. So the centroid is given by 1/3 of h. Centroid of the triangle is 1/3 of h from the base. From the base it is 1/3 of h. So from the left end, x minus 1/3 of h. Total length minus 1/3 of h. Like this. So first we find out the net force, then we consider the centroid. At the centroid, you will be having the force acting, okay, the position of the force. So for variably distributed loading, UDL and VDL. So we have to convert UDL as well as VDL into a single point load, single concentrated load. Okay. So for UDL it is simple, just at the middle of the length we will fix the force, position the force. Whereas for VDL, we consider the area. Maybe sometimes we have a trapezoid, combination of a triangle and rectangle. So we can split the areas and we can find out the equivalent force, single equivalent. Okay. So you can note down the two cases. Case 1 and case 2. இந்த ஏரியால ஃபுல் லென்த் இருந்துச்சுன்னா லென்த்தோட இருப்பாங்க. அதான் சொன்னேன். So we have a problem. Listen. So now I have combined the areas. We have a trapezoidal area in the first portion from A to B, then a rectangular area of UDL. Okay, so this is the combination of VDL and UDL. So we have to find out the net force, resultant force acting on the beam. Okay, so we can resolve it into two ways. There are two methods you can follow. This is the support. I expect no talking. So these are the supports A and B. So the beam overhangs here. This is the loading we have. We can split it into two areas. So this one is thrown from point A until the end, point C. You can consider it as rectangle whose height is 3 kilonewton meter. Okay. So this is the UDL. On the top of UDL, we have a VDL. So this is 3 kilonewton meter. This is 0. So like that. So we can add the two. We will get two resultants first. Two resultants. Resultant for the triangular VDL and resultant for UDL. Okay, so you say FR1 will be 3 times 6 throughout the length. Okay, 6 kilonewton meter. 3 times 6. So 18 kilonewton is the net force for area of what? Rectangle UDL. Okay. This is 2. So FR2 3 into half 3 into the height 4.5. How much it will be? 6.25. 6.7. Okay. So what are the positions of these forces? So FR1 will be acting at the middle of 6 meters length. Okay, at 3 meters. At 3 meters, you will have FR1. Sorry. At 3 meters, you will have the first force FR1. And the second force FR2 will be half. Sorry, 1/3 of height, 1/3 of 4.5. That is 1.5. This time we will have FR2. This is 1/3 of pitch. From the base of the triangle, I consider this as the base. This is the height along which we have to find the position of centroid. So I consider this as the height. So 1/3 of height. Okay. 1/3 of 4.5, that is 1.5. So from the base of this triangle, I consider acting at this distance 1.5 meters. The FR2 is acting. Now we got two forces. We have to find out the resultant for the two forces. Okay. So the two forces are vertical only. There is no horizontal component. There is no inclined one. So we just say sigma FR1, sigma FR will be FR1 plus FR2. So add the two forces, 18 kilonewton plus 6.5 kilonewton, 24.75 kilonewton is our net force. And how will you find out its position? In order to find out its position, we have to write the moment equation. We have to go for moment equation. Okay, in order to find the position of the resultant of 2 point loads, we have to find out the moment equation. So first find the moment for FR1. FR1 times about point A times 3. Okay, then it is acting in the counterclockwise direction, clockwise direction, so negative sign. We use this convention counterclockwise positive. This is also in clockwise direction. So FR2 times 1.5. Okay. This will be equivalent to the total moment sigma MO. M about A. Moment about A is FR times T. So this is equivalent to this value. You can find out the D distance. First, we find moment of each force and sum of them. Moment of force FR1 from point A. So moment, its perpendicular distance is 3 meters. Perpendicular distance 3 meters. So force is here 3 meters. So it will have a rotation in clockwise direction. So it is negative. Similarly, if you consider FR2, this is FR2 times 1.5 meters. Again clockwise. So clockwise means negative. Okay. So the two forces will give you a negative moment. So this is equivalent to moment produced by the resultant of the two forces. Moment produced by the resultant of two forces. The resultant of two forces 24.75 kilonewton. It produces moment, and we can write that equation as FR times D, perpendicular distance. Okay. So you can find out the D position at which the resultant moment will be acting. So resultant moment 24.75 will be acting at distance D. So 3 steps. First, we find out resultant for the distributed loading and variable loading. Then moments for the distributed and variable loading equated to the resultant of the forces times the distance, perpendicular distance. We can find out the distance. Okay. You can note down. 2 point. D will be 2.5 meters. The D you can find out FR1 times 3 that value. Then equate it to 24.75. Okay. You want the exact answer?
1 by 3 into 4.5.
1 by 3 into 4.5.
How 6.5?
1.5. Six 6.75 is no, this is
2.60. Sir, how sir right?
How?
Right.
Final answer. Minus if you get the moment in the opposite moment negative means what you ask him to mean. Yeah. Triangle height, this is considered as the height. This is the breadth.
Sir, FR1 and total FR1 minus
FR1
minus FR1 minus FR2.
So the minus 24.5. 24.7. half 3 into 4.5, 6.75.
Given
No, we are finding out.
for height.
No,
How sir?
13.75 or 13.5 or 11, so it's 6.7. சொல்லும்போது கவனிக்கணும். திரும்ப I will explain again. Listen. புரியாதவங்க கவனிங்க. Okay. I will explain again. So first we split it into two areas. A rectangular area and a triangular area. Is it okay? கவனிக்கிறியா? சொல்லும்போது கவனிக்க மாட்டீங்க. அப்புறம் டவுட் கேட்டுருப்பீங்க. So we split into two areas. The total length of the beam is 6 meters. 4.5 up to from point A to point B 4.5. This is 1.5, so 6 meters. This is 4.5 meters. This is 1.5 meters. Total length is 6 meters. So first we consider this rectangular UDL. So FR1, we find out the resultant for the UDL. That is, you can say 3 kilonewton per meter is the given one. So 3 kilonewton per meter times 6 meter. Okay. So we get this meter cancel. We get 18 kilonewton as FR1. Resultant for UDL. Then we go for resultant for VDL, FR2. So the VDL is triangular. VDL is triangular. It is half. BH is the area. Half. Say B is 3. I am considering the triangle is just lying on rectangle. So this is the breadth and this is the height I am considering. So 3 times 4.5. So this is 6.75 kilonewton. Okay, 6.75 kilonewton. So after that, we find out the resultant of the two forces, FR, summing up the two forces. Okay, so we write it as FR1 plus FR2. So it will be 18 plus 6.75. So it will be 24.75 kilonewton. Resultant of the two forces. Okay. Now we have to find out position of each UDL. So we got the magnitudes of FR1, FR2 and its resultant. Now how to go for position of FR1? Position of FR1. So FR1 is a rectangular area, you can say at the midpoint of the length, middle of length of the beam, that is 3 meters, middle of the length. So we have FR1 acting here at 3 meters distance. FR1 at 3 meters distance. Now FR2. It will be at the centroid of the triangle. Centroid of the triangle is 1/3 of height. 1/3 of height. I said this is the height. I have considered this as the height. This as the breadth. So 1/3 of height will be 1/3 of 4.5. 1.5. So from here at 1.5 meters we will have FR2. So we got the position for FR1 and FR2. Now we have to find out the position for FR also. The single, we have to convert all the forces and moments into single equivalent force. So to convert these two forces into single equivalent force, we got the magnitude now. To find the position, we take moment of each force FR1 and FR2 about point A. This is point A. About point A. So moment of point A. So I say moment of Fr1 about point A first. Force 1. The force 1 about point A, that can be obtained as Fr1 times its perpendicular distance 3 meters. Fr1 and its perpendicular distance is 3 meters. Okay, so T1 I write it as how much? 18 kilonewton times 3. Hello? 54 kilonewton meter. 54 kilonewton meter. Similarly, if you write moment of second force, force 2 about A, this is Fr2 times T2. So Fr2 is 6.75 times 1.5. How much it comes? 10.75. But according to the sense, okay, they have a clockwise rotation, so it will be, we can write it as clockwise, 54 kilonewton meter clockwise. This also clockwise, or you can have it as negative. After that, you add up the, in order to find out the resultant, okay, resultant moment, sigma m about A will be 54 plus 10.125. So 64.125 kilonewton meter clockwise. Both are in the same direction. So this is our resultant moment. Okay, resultant moment is produced by the resultant force. So this resultant moment is equals to Fr times T. Fr times T. Or we can say 64.125 is Fr times T, and T is 64.125 divided by 24.7. Okay. So we will get T value.
2.5.
So we got the position for Fr. Okay. Moment about A, all are moment about A. We consider the same point. We convert, transmit all to a single point. Moment about A. Okay, now listen. Actually, we have to analyze the equilibrium of rigid bodies. That is the topic of our unit. Okay, in order to go for equilibrium, first we have to consider the free body diagram. We have to draw the free body. If you remember what we did in our equilibrium of particle, we first find out the free body diagram. What is the free body diagram? It's an isolated object, diagram of an object, which shows all the forces acting on it. So we have to consider a path which accounts for all the forces. In the particle case, the particle may be a hook, okay, which is pulled by many cables. So the cable is one body, one object. Hook is one object. The end which it is connected is one object. So if we draw the free body diagram for each object, one may represent one force or two forces. We consider an object which has maximum forces. We consider an object which has maximum forces. Okay, so that we take it for equilibrium condition. Okay, we consider sigma Fr equals to 0, sigma m equals to 0, like that. Here the same approach is followed here, but here we have a rigid body. Why we assume rigid body? And that is important. Okay, in rigid body the points remain same. So the application of force and the line of action of force is not altered if you consider it as a rigid body for equilibrium condition. Okay. So we have to draw a free body diagram. the diagram is the sketch of outline shape of the body which is isolated from the surroundings. It shows all the forces. It shows all the forces and moments acting on the body. It should account for all the forces. If you say all the forces, applied forces are there, then reactions also there. We have applied forces. We apply some force according to Newton's third law of motion. An action will produce a reaction. Okay. So if you apply some force, there will be some reaction also. So a free body diagram should represent all the forces, known and unknown forces. Say applied forces are known forces, forces which are developed. Okay. So we have to consider for known forces as well as unknown forces. Forces applied are known forces, forces which are developed due to the applied force. An action which produces a reaction. Those will be the unknown forces. That will account for all the forces. Okay. So in order to consider the unknown forces, we must know about the support reactions. Reactions produced by the supports. A beam on any body, any object, any rigid body will have some support. Without support, it cannot remain in the space. Okay, there should be some support, some way it is be supported. So any support will have some reactions because of the weight of the body. Even if there is no applied force, if a body is restricted to move, okay, whenever you are restricted to move, you try to resist this. So that resists the restriction. If you say you should not go out of the hostel by 9 o'clock, we try to come after 9 o'clock. We try to trespass that, isn't it? So in the same way, if you are restricted to do something, you try to resist it, that we call it as reaction. So if your translation is arrested, it will produce forces. If the translation of a body, if the to and fro motion of the body is arrested, they are constrained. The restriction will produce a force. If the rotation is arrested, if the body is not allowed to rotate, then it will produce moment, reactive moment. So we will have a reactive force as well as reactive moments. All together we call them as reactions, support reactions. A support is arranged in such a way, if translation is not allowed, it will produce a force. If the rotation is not allowed, moment will be developed. Reactive moment will be developed. So a body in the space will have 6 degrees of freedom. So we will have 3 translations and 3 rotations. Translation along x, y and z. Rotation about x, y and z. Okay. So on what type of constraint we have, the reaction will be developed in a particular manner. So if it is not allowed to translate, it will produce a force. If it is not allowed to rotate, it will produce a moment. Consider some of the supports. We have a beam supported at the end by a roller. Okay, we call it a roller support. It restricts translation in y direction. Vertical movement is arrested. Okay, we have this is the beam. A roller is placed at the end. Okay, end. So the roller will not allow the beam to move in y direction. It cannot move in y direction. So what happens? A reactive force in y direction will be developed. Reaction force in y direction will be developed. A roller. We can say this kind of beam as simply supported beam. Beams can be classified in different manner. A cantilever beam, you would have heard. A cantilever beam means it's held in one end of the beam, the other end is free. It's hanging, overhanging like this. That is called cantilever beam. The simply supported beam will have a simple support at 2 points, at the 2 ends. It will not allow the beam to move in y direction only. There is a free movement in the x direction. So this kind of beam arrests y direction movement, translation. So there is a reactive force. This joint, can you see, it is a pin joint. Okay. So what type of restriction we get? It's a hinged joint. Hinge. There is a hinge. Rotation. So it can rotate. It can rotate. Translation? Restricted. It cannot translate in y direction as well as x direction. X and y translations are arrested. but free rotation is there. Free rotation is there. Okay? Hinged or pinned support, restricted translation in X and Y direction. So reactive forces in X and Y directions are developed. Reactive forces in X and Y direction. Okay? So translation is not allowed in X and Y direction. So as there is a restriction, forces are developed. Reactive forces. Okay, next kind, we have a fixed support. So what type of reaction we'll have? What type of restriction we have? It cannot translate, it cannot rotate. No translation in X and Y direction. Say it is a coplanar system. Okay, we consider only the X and Y, neglect the Z direction at present. Okay, so we have only we say only X and Y. Okay. So it is a fixed support. No translation in X and Y. No rotation around X and Y also. Around Z. So it restricts the translation X and Y direction, and also no rotation around Z direction. So the sign convention is arbitrary. Okay, at present we put it upward or downward. It depends on the way it is being moved or applied. So we just say moment is developed. Whether it is upward or downward, that we can decide only later. Depends on the force, nature of the force we have. Okay, arbitrarily we put as counterclockwise, but it is not exactly true. It should be counterclockwise only or clockwise only. Just the moment is developed. Okay, reactive moment is developed, and two forces are developed. So to account for the direction of the force, we have to depend on the applied forces. Okay, that we will see here. Sense of force and sense of moment, we cannot decide now. There is no applied force shown. So we will have similar type of reactions. We have a cable. So the cable will restrict motion in this direction. So the reactive force is developed. A pin joint, roller. There is another two pins are there. It will have the same effect as a pin joint. A slope. A slope is there at the end. So slope will, the perpendicular to the direction of the slope will have a reactive force. Perpendicular to the direction of the surface which is in contact with our member, it will have a force. Perpendicular to the direction of the slope. Okay. So there it is a fixed beam. We have few more. We have a link, weightless link, or a roller here. Roller, maybe 2 or 3 rollers. Same effect. Perpendicular to the direction of the slope will have a restriction. Or a roller maybe like this, a single roller, or a ball, rocker, smooth connecting surface. So it can slide in this direction, but it cannot move. It is hinged also. It is a fixed case. So different pins are there. According to the type of restriction we have, the movement, the reactive moments and reactive forces will be developed. Suppose if we consider a system in 3D, okay, we have a bearing, a shaft is provided with some collar at both the sides of the bearing. So it will have only rotation. It can rotate around your x-axis. So what type of, so there is only free rotation around x-axis. So if you consider all the 6 degrees of freedom, we will have all the 3 reactive forces. No translation in x, no translation in y, no translation in z. Okay, no translation, and no rotation around the z, no rotation around y also. Okay, so 2 moments and 3 reactive forces will be developed. So if you draw the 3-body diagram for the first part, the shaft and collar, this is the first integral part, the 3 axes. So no rotation, no translation in x, y and z. So forces, reactive forces are developed. The sense of the forces arbitrarily given. Okay, it need not be upward or downward, arbitrarily given. and there is a reactive moment about Y, it cannot rotate like this. It cannot rotate. The bearing will restrict rotation of the shaft around Y. It cannot rotate around Z also. It can rotate only about X. So we will have two reactive moments. Similarly, if you consider the free body diagram of the bearing, you will have opposite direction. Same moments and forces in the opposite direction. Okay. So if you assemble them, two forces will cancel each other, two reactive forces will cancel each other, it will be in equilibrium. So they are not moving. Okay. So if you consider the free body diagram separately, we will show the reactive forces. If you assemble them to the actual support or whatever it be, the cancellation of forces will happen and it will bring the system to equilibrium. So these are called counter forces. So Fz for the part 1 is acting upwards. If you consider this as upward means this will be considered as downward. So if you sum up, the two will get cancelled. Similarly, X and Y forces also. For one part, it will be in the one direction means the other counterpart, which is the assembly, where you are going to assemble it, will have the force, reactive forces in the opposite direction. So what will happen to this type of bearing? There is no collar. There is no collar. Where it will, what type of degrees of freedom? How many reactive forces we will have? How many reactive moments we will have? It is free to rotate as well as translate in X direction. Okay, it can rotate and translate. There is no collar, no restriction for translation. So it can freely move on X direction. So only translation in X, Y and Z will be there. Reactive forces in Y and Z will be having and two moments will be there. Whereas this case is similar to case 1. It can, but there is a difference. It cannot rotate. It can only translate. It can only translate. So 3 moments and 2 forces will have. So we have one object over the other like this. It can rotate in Z direction. Rotation in the Z direction is only allowed. Okay. One slab over the other slab. 2 slabs are there. Translation in Z direction restricted. Translation in X and Y, okay, possible. So you have one reactive force and 2 moments. One reactive force. What about the last case? A ball and socket joint. It can rotate in all the directions. Rotation around X, Y and Z possible. No translation. No translation is possible. Okay. So according to the degree of freedom, the way it can move, you will have reactive forces. If it is having degrees of freedom to move in one particular direction, no reactive force will exist in that direction. Okay. So this is about the reactive forces by drawing the free body diagram. Now we will come to the actual problem. With that we will conclude. Okay, I will just show it. We have a fixed beam acted upon by a point load 1200 Newton. The length of the beam is 6 meters. So this beam is called cantilever beam. Okay, it's fixed at one point, free at the other end. Cantilever. Okay, so if you draw the free body diagram for the beam, first step is we have to draw the free body diagram for the beam. So at the end A is restricted to move as well as rotate. No translation and no rotation for end A. End B is free to rotate, free to move. Okay, end A is restricted. So we have, say, consider coplanar system of forces. We will have motion in reactive forces in X and Y direction, and also moment about Z. Moment about. So this is the force applied. Effect of applied force. So it shows all the forces acting, known forces and unknown forces. 1200 is the known force. Reactive forces and moments are unknown. And also the weight is given. Suppose if the weight of the beam is given, we can write down that also. Effect of gravity of the beam. Okay. So this is another case a fork lifting crane is lifting two rollers, hollow pipes. So what kind of reaction they will have? Okay. So the fork develops some restriction for the cylinders to move. So perpendicular to the contact surfaces, we will have reactive force. So if you consider first roller will have load, okay, weight of the roller, effect of gravity, then restriction from this surface, perpendicular to this surface, one reaction, then another roller B will produce another reaction, the second half will, so we have three reactive forces and also weight. There is no moment, it is free to rotate, okay. So we consider only coplanar system of forces and moment. So restriction from this surface, restriction from this surface, restriction from the other roller. So three reactions here. If you consider roller B will have restriction from this surface, restriction from roller A. So all together we have system of reaction. Okay. So we will have some more portion left. We will cover it in the next condition for equilibrium and how to obtain the values of reactive forces, support reactions, support moments, that we will see in our next class. Okay.